So today we're talking about orthogonal projections, which is actually kind of an extension of something that we've already done, that we did last class. So last time we talked about how to take a vector y and project it onto a line. So a line is basically a subspace with dimension 1 because the basis is only one vector. And so the line is every multiple of the vector. Today we're going to ask the question, how do we project a vector onto a subspace that has dimension greater than 1? So now the basis is made up of just more than just one vector. So consider the situation. We have five orthogonal a basis with five. Let's try it again. This is an orthogonal basis for R5. Okay, so it's a basis for all of R5. Notice that there are 5 vectors, so that's good. It's an orthogonal basis, which means that each of them is orthogonal to the others. And then we're looking at some other vector y, which is an R5. Now let's consider a subspace where we're spanning, where the subspace is the span of just 2 of those 5 vectors. Now we know that y can be written as a linear combination of all 5 because of course y is in R5. And so what I'm going to do is I'm going to rewrite that as just the 2 terms that are in W, the 2 terms that are from the vector that are the basis for W, plus everything else. And so the first part I'm calling Z1 and the second part I'm calling Z2. Now certainly Z1 is in W, and we can see that because W represents the is the span of U1 and U2. In other words, W is all vectors that are the linear combination of U1 and U2. So Z1 is that linear combination, so Z1 is in W. What we want to show is that Z2 is in the subspace that's orthogonal to W, or W perpendicular, that we defined last class. So, and what we said last class was Z2 is in W perpendicular if Z2 is orthogonal to both of the vectors that are the basis of W. So basically all I need to do is show that Z2 is orthogonal to U1 and show that Z2 is orthogonal to U2. And so we do that with dot product. So Z1 dot U1. And so if I do that, let's see, so Z1 is, I'm sorry, I'm trying to show Z2 is orthogonal. So Z2 dot U1. So Z2 was C3U3 plus C4U4 plus C5U5. And if I distribute, and I'm sorry, we're dotting that with U1. And so if I distribute that, we're going to get C3 times U3 dot U1 plus C4 times U4 dot U1 plus C5 times U5 dot U1. Now, here's where we're going to use the fact that this is an orthogonal basis. This trick is only going to work if the basis that we have is an orthogonal basis. Because if this is orthogonal, U3 and U1 are orthogonal, which means that this term is going to be 0. U4 and U1 are orthogonal, so this will be 0. And U5 and U1 are orthogonal, so this is 0. So that the whole thing is 0, which means that Z2 is orthogonal to U1. If I did Z2 dot U2, I'm going to get the exact same result. And so we're also going to get an answer of 0. So Z2 is in the W perpendicular. Now notice that Z2 is basically the linear combination of U3, U4, and U5, which means that I could define W perpendicular as just the span. Basically, W perpendicular is the span of all the other basis elements of R5 that were not used to create W. So if W is the span of a couple of those vectors, W perpendicular is the span of the rest. In this case, U3, U4, and U5. Okay, now this is going to help us to come up with a way of, as I said, finding a projection of a vector y onto the subspace W. And so we've got what's called the orthogonal decomposition theorem. So let's define W as this subspace of Rn. Again, here it doesn't have to be 5. It could be anything. And then we're going to say that every vector y in Rn can be written uniquely in a form where y can be written as y hat, which is in W, and z, which is in W perpendicular. So if y is any vector in Rn, it can be written as the sum of a vector that's in our subspace and a vector that is orthogonal to that subspace. And then, of course, the question is, how do we find those things? Well, y hat is going to take this form. Now, I'm not going to go through the whole process because it's going to be very similar to what we did last class. I want to point out that if I were to stop here, if W had a basis with just one vector, this, what I just circled there, is going to be y hat. And that, I mean, that's what we did last class, right? Last class, we were projecting it onto a line, meaning a subspace of dimension 1, and this was the result. Well, if the dimension is bigger than 1, we're just going to have these extra terms to consider here as well. So it's going to be the same format, same idea as we did last class. Just now there's more of them because now W is defined by more than just one vector. And then to find z, we're just going to solve for z, and we get y minus y hat. Okay, and in the picture here, we can kind of see what we're talking about. Here's vector y, and we're projecting it onto W, and so this vector right here would be y hat. And then z is going to be orthogonal, so that's a little right angle here. Yeah. So that's the picture. Again, it's the same picture as last time, except this time, instead of projecting it onto a line, we're projecting it onto a more complicated subspace. Y hat is called the orthogonal projection of y onto W, and is sometimes written as projection onto W of y. So just a little nomenclature there. Okay, so let's let these two vectors be an orthogonal basis for W. By the way, we're told it's an orthogonal basis, but it's worth pointing out that we could actually do the dot product. I'm going to call these U1 and U2. If I were to do U1 dot U2, we get -4 plus 5 minus 1, which is 0. So they are orthogonal, but of course we're told that. We don't have to check. We want to write y as the sum of a vector W and a vector in W and a vector in W perpendicular. So the formula from the previous slide said y is equal to, so it was u1 dot y over u1 dot u1 times u1 plus u2 dot y over u2 dot u2 times u2. So let's see, u1 dot y would be 2 plus 10 minus 3, which is 9. U1 dot u1 would be 4 plus 25 plus 1, which is 30. Times u1, which was 2, 5, negative 1. And then let's see, u2 dot y would be -2 plus 2 plus 3, so that's 3. Over u2 dot u2, which is 4 plus 1 plus 1, which is 6. And that's multiplied by u2, which is -2, 1, 1. Okay, let me simplify this a bit before we come up with an answer here. This would be 3/10 times 2, 5, negative 1 plus 1/2 times -2, 1, 1. Okay, and just in this case, I think it's going to be more convenient for us to work with decimals rather than fractions. So we got 0.3 times 2 would be 0.6. 0.3 times 5 would be 1.5. And 0.3 times -1 would be -0.3. Should have left myself more space. Oh well. Half of -2 is -1. Half of 1 is 0.5, and then 0.5. Finally add these together, and I'm getting negative 0.4, 2, and 0.2. Okay, so there's my y hat. I'm sorry, I wrote it wrong at the beginning. I apologize. Okay, that should have been y hat. Sorry about that. And so then z is y minus y hat. So y is 1, 2, 3. Y hat was negative 0.4, 2.2. If I do the subtraction, I'm getting 1.4, 0, and 2.8. So finally, my vector y can be written as y hat plus z. 1.4, 0, 2.8. Okay, so there's our projection of y onto w. Okay, so one of the questions we might want to consider asking is, well, okay. One of the things we might consider asking is why? Why would we do this? I don't know if I have a great answer for this, but maybe a better way of phrasing that would be, what does y hat tell us? What does y hat do for us? And so for that, we've got what's called the best approximation theorem. It says that basically y hat is the vector in w that is closest to y. Meaning that so here's my vector y. If I were to pick any vector in w, the one that's going to be closest to y is going to be this y hat. Any other vector, if I call v any other vector in w, remember this is, when we do y minus y hat, the magnitude, this is the distance from y to y hat, and this is the distance from y to v. Notice that, this is basically saying that the distance to y hat is less than or equal to the distance to v. And the only way they'll be equal is if v was actually y hat. And so we could say that y hat is the best approximation of y by elements of w. Now, I want to point out, before we get to the next little bit here, I want to point out that in this lesson, we've been using an orthogonal basis. But remember, w could have any basis. I mean, there's lots and lots of bases. We know that the dimension is, well, actually, I mean, I guess what w is, but whatever the dimension is, like, let's say the dimension is 3. The basis would be made up of 3 vectors, but that basis is not unique. There's lots of bases that could describe the same subspace. So w could have any basis, right? They would all just have the same dimension. The point I'm trying to make here is, because we haven't discussed the basis of w, this means that y hat is the same no matter what basis we use for w. If y hat represents the vector that is closest, or the vector in w that's closest to y, that's going to be true no matter how we describe w. My reason for pointing that out is, if we had an orthogonal basis, we now see there's an easy way to find y hat. We've got a formula for it. If we don't have an orthogonal basis, y hat still exists. It's still the same vector. It's just that without an orthogonal basis, it's a lot harder to find. Y hat. So notice that having that orthogonal basis is very convenient. And in fact, if we had a basis for w that was not orthogonal, we would need to, if we wanted to find y hat, we would first need to find a new basis that is an orthogonal basis. And in fact, that's going to be the focus of the second part of this lesson. Anyway, so this is what y hat is. All right, so let's find the distance from y to this subspace w, which is the span of these two vectors. And one more time, I want to point out, no, this is different. I want to point out that this is an orthogonal basis. We're not told this time, but we could check it and see that it is. Again, let me just call these U1 and U2. Notice that u1 dot u2 would be 5 minus 4 minus 1, which is 0. So these are orthogonal vectors. So it's an orthogonal basis. That's cool. So if I want to find the distance from y to this vector space or subspace, what I really mean is find the distance from y to the vector in the subspace that's closest to y. Okay, think of it this way. This might be a little silly, but let's say you're standing in the middle of, I'll erase this in a minute, but let's say you're standing in the middle of a field, okay, and there's a street, and you need to walk to the street. And so your question is, what is the distance from you to that street? Well, I mean, what do you mean? Do you mean this distance or this distance or this distance? When we find the distance to a line or a plane or a subspace or whatever, the distance is always the shortest distance. And the shortest distance is this perpendicular distance. So if I want to find the distance to a line or my arm fell off, that's weird. If I want to find the distance to a line or whatever, what I really mean is I want to find the distance to the point on that line that is closest to where I am. That closest point is can be found with that perpendicular segment or that orthogonal vector. And so really what I'm asking is, if this happens to be y, this vector here is going to be y hat. Okay, so this is just justifying why we're using y hat, but basically that's what we're going to do. We're going to find y hat, and then I'm going to find the distance between those two vectors. All right, let me erase all that. So again, this was u1 and u2. Okay, so y hat is u1 dot y over u1 dot u1 times u1 plus u2 dot y over u2 dot u2 times u2. Okay, we already did this, so not this problem, of course, so we still have to do it again. So u1 dot y would be negative 5 plus 10, which is 15. u1 dot u1 would be 25 plus 4 plus 1 is 30, times u1, which is 5, negative 2, 1. And then u2 dot y would be negative 1 minus 10 minus 10, so negative 21, over u2 dot u2, which is 1 plus 4 plus 1, which is 6, times u2, which was 1, 2, negative 1. Okay, so I'm getting, so that's, here, let me write it out. So I've got 1/2 times 5, negative 2, 1, minus 7/2 times 1, 2, negative 1. Okay, and again, if you want to use decimals, that's cool. I'd get it. I think this one, the fractions aren't too bad. We're going to get 5/2, negative 1, and 1/2, minus 7/2 to 7, negative 7/2. And so if I then do the subtraction, I'm going to get 5/2 minus 7/2 is negative 2/2, or negative 1. Negative 1 minus 7 is negative 8. And it'd be 1/2 plus 7/2 is 8/2, which is 4. So there's my y hat. So this would be the point in W that's closest to y. Now I need to find the distance from y to that point. So y minus y hat. By the way, you can subtract these back the other direction. It doesn't matter. So y minus y hat is going to give me the vector 0, 3, 6. And then finally, the magnitude of that is going to be the square root of 0 plus 9 plus 36, which is the square root of 45, which if you're going to want to get really fancy is 3 radical 5, but it doesn't matter. The point is, this is now our distance between those two vectors. Okay. Next up, what if, instead of an orthogonal basis, what if we had an orthonormal basis? Now remember, orthonormal means not only are the vectors orthogonal to each other, also they are all unit vectors. And what that means is, if you take any vector and dot it with itself, you're going to get 1. So all these denominators no longer matter. So orthonormal makes the formula a little bit easier. And so here's what I wanted to work on now. I'm going to define U as being the matrix where each column is made up of those vectors in the orthonormal basis. And I'm claiming that y hat is U times U transpose times y. So let's see why that is. Okay. Now let me rewrite this a little bit more here. Y hat is equal to y dot U1 times U1 plus y dot U2 times U2 plus dot 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 plus y dot UP times UP. Okay. Now, notice that those vectors that are separate here, U1, U2 up through UP, those are the vectors in U. My point is, and then notice that each of those then has a weight or a coefficient. This dot product, this dot product, this dot product. So think about that. If we've got the columns of our matrix multiplied by weights, that's the same as saying this is our matrix multiplied by some vector, where that vector, let me move that over a little bit. Okay, so this is our matrix times some vector, where that vector is made up of each of those weights. So this would be U1 dot y, U2 dot y, and so on up through UP dot y. And I switched them in on purpose. I'll show you why in just a minute. Okay. Now, so that's the question now becomes, what is V? Now, let's remember that U1 dot y, another way of writing that, right? This is how we define the dot product. But another way that we wrote that was by writing it as U transpose times y. This is not a dot product anymore. This now becomes a matrix multiplication. So notice that now I'm taking U transpose, which if U is a vertical vector, now U transpose is horizontal. I'm taking that horizontal vector, I'm sorry, that should be U1. I'm taking that horizontal vector and multiplying it by y. In other words, I'm now making U1 transpose the top row of a new matrix, and that's being multiplied by y. Because then, again, if I think of this as, remember, U1 is a matrix, is a vector. So this is a big full matrix. This whole matrix, the top row is U1 transpose because it's sideways. And so then when I do that when I multiply that top row by y, I'm basically doing the dot product. And then we have U2 transpose on down to UP transpose. And this matrix right here, that's U transpose. So what we're finding is that this vector V that we were working with over here is nothing more than U transpose times y. And so y hat is this product. So there we go. Let's see how we could use that. Let W be the span of these two vectors. Please note it is orthogonal. And let's find a vector, find a matrix A such that the projection onto y, W of y is equal to A times y for any vector y. Please remember that this is just another fancy way of saying y hat. And so we want to find a vector, or a matrix A, so the y hat is equal to that product times y. Well, we already know that y hat is equal to u times u transpose times y. So this product is really what we're looking for. That's the matrix A that we're being asked to find for this problem. Now, I want to point out that, yes, this is an orthogonal orthogonal basis. I'll call this V, call this W. But while it is orthogonal, it is not orthonormal. So to get that, I need to also find some magnitudes. So V, the magnitude of V is going to be the square root of 1 plus 0 plus 1, which is the square root of 2. So my first orthonormal vector is going to be taking V and divided by radical 2, and so that would be 1 over root 2, 0, negative 1 over root 2. If I find the magnitude of W, it's going to be the square root of 0 plus 1 plus 0, which is just 1. So my second orthonormal vector is going to be just W itself, just divided by 1. Okay, so from those, I'm getting that U, the columns of U are my two orthonormal vectors. So 1 over root 2, 0, negative 1 over root 2, and 0, 1, 0. So there's U. And so when I do, so for the matrix A that I'm looking for, it's going to be, again, U times U transpose. So U is that matrix, 1 over root 2, 0, negative 1 over root 2, 0, 1, 0, times U transpose. Now remember, that means that the first row of U becomes the first column of U transpose. The second row becomes the second column. The third row becomes the third column. Please notice we have a 3 by 2 matrix multiplying a 2 by 3 matrix. So my result here is going to be 3 by 3. If I take my first row, multiply by my first column, I get 1/2. First row times the second column is 0. First row times the third column is negative 1/2. And then 0, 1, 0. And then finally negative 1/2, 0, 1/2. Okay, and so that's the matrix we're looking for. That's that matrix A. Okay, now, as I mentioned earlier, W could have any basis at all, but as we found today, it's really useful to have an orthogonal basis. And so for a variety of reasons, but for whatever reason, having an orthogonal basis is useful. If we're given some other basis, any basis, again, it doesn't really matter. If we're given any basis, it's possible to find an orthogonal basis using something called the Gram-Schmidt process. In other words, it allows us to take some basis made up of vectors x1, x2 up through xn and convert it to an orthogonal basis, and those vectors I'm going to call v1, v2 up through vn. So that's our goal here, is how do we find that? So here's the Gram-Schmidt process. First of all, and remember, all the x's were the original basis, all the v's are the orthogonal basis. And here's how Gram-Schmidt works. I'm going to start by just assuming my first v is the same as my first x. It doesn't matter. Okay, you can start with whatever you want. But now keep in mind v2 has to be now orthogonal to v1. Well, we know how to find a vector that's orthogonal to another vector. Remember, that was our z, right? I'll erase this in a second. But basically what we need to find is, if we need a vector that is orthogonal to x, that's z, which is basically x2 hat, or x2 minus x2 hat. And here's x2 hat, and this is my formula for x2 hat. And again, I'll erase this in a minute. But that's the idea. Z was that vector that was orthogonal to the other one. So let me erase this. So the answer is, we're looking for a vector that's orthogonal to the original one. Okay, now visually this is what it looks like. If this is my first vector v1, I need this vector v2 that's orthogonal to it. Okay, yeah. Now let's talk about v3. To find v3, I need a vector now that's orthogonal to the first two. In other words, I need a vector that is now orthogonal to this vector space W that I've got drawn over here, that's defined by v1 and v2. Well, now I need a vector that's orthogonal to a vector, to a subspace. This is what we did today, right? This, again, it's z, the z that we've been working with today this time. This, all of this would be, well, this whole thing, I guess I should say, is now x3 minus x3 hat. Okay, this was the z that we worked with as part of today's lesson. And visually, this is what it looks like now. If W, we're calling this W2 down here, is the span of V1 and V2, don't worry about that prime here right now. We'll address that in a minute and just basically say that it doesn't matter, but that's okay. So if W2 is this vector space that's the span of these first two vectors, V3 is this vector that's orthogonal to the first two. So this process allows us to do this. Okay, so let W be the span of these two vectors. Let's find an orthogonal basis. Okay, so I'm going to call these x1 and x2. So again, I'm going to let v1 just be x1. So that's just 3, 6, 0. v2 is equal to, let's see, we said it was x2 minus x2.v1 over v1.v1 times v1. Okay, so x2 was, let's see, 1, 2, 2 minus x2.v1 would be 3 plus 12 plus 0, which is 15. v1.v1 would be 9 plus 36 plus 0, which is 45, times v1, which was 3, 6, 0. So I'm getting 1, 2, 2 minus 1/3 times 3, 6, 0. So I'm getting 1, 2, 2 minus 1, 2, 0, which gives me my answer of 0, 0, 2. Okay, so W could also be written as the span of these two vectors, 3, 6, 0 and 0, 0, 2. And if you were to do the dot product, certainly these two vectors, the dot product would be 0. Whereas the original basis, the dot product was not 0. Okay, so there's my orthogonal basis. Let's try another one here. This time we've got 3 vectors in our basis. Let's, again, same question, find the orthogonal basis. So I will define these as x1, x2, x3. So v1 is just x1, which was 1, 1, 1, 1. v2 is equal to x2, which is 0, 1, 1, 1, minus, let's see, it's x2.v1 over v1.v1 times v1. So we've got 0, 1, 1, 1 minus, so x2.v1 is 3 and v1.v1 is 4 times v1, which was 1, 1, 1, 1. Okay, so I've got 0 minus 3/4, so negative 3/4. 1 minus 3/4 is 1/4, and then I just do that a couple more times. Okay, so there's a v2. Now, let's keep in mind something important here. This is v2, and that's great. But remember, what was v2? It was a vector that was orthogonal to v1. Okay, well, wouldn't that be true if instead of using v2, we were to use a multiple of v2? And I mention only that because the fractions are not very fun. And so rather than using v2, I'm going to use a new vector that's basically just take v2 and multiply it by 4. So you get negative 3, 1, 1, 1. Now, a lot of times it doesn't matter, but we're going to be using this answer, and so I'd like a simple answer. The book, I mean, technically it's not the same as v2, so they call this v2 prime. I'm just going to call it v2. It doesn't matter. Honestly, I've got enough to worry about without keeping track of all those primes, so I'm just going to leave that as v2. But yeah, so we can simplify, because again, the important part is the direction, that we're orthogonal to v1. All right, v3 is equal to x3 minus x3.v1 over v1.v1 times v1 minus x3.v2 over v2.v2 times v2. Okay. So we've got 0, 0, 1, 1, close that, minus. So x3.v1 is 2, v1.v1 is 4, times v1, which was 1, 1, 1, 1, minus x3.v2 is 2 over v2.v2, which is 3, times v2, which is negative 3, 1, 1, 1. If I combine all this, let's see, we're going to get 0, 0, 1, 1, minus 1/2, 1/2, 1/2, 1/2, 1/2, minus, now I'm only bringing the positive 2/3, so it'll be negative 2, 2/3, 2/3, 2/3. Okay, and if I put all those together, yeah, if I put all those together, so negative 1, wait, yeah. If I put all those together, we're going to get 0 minus 1/2 plus 2, which is 1.5. Negative 1/2 minus 2/3 is negative 7 over 6. We have 1 minus 7 over 6, which is, wait, 1 minus 7 over 6 is negative 1/6. And then I'll do that again, we get another negative 1/6. Okay, I feel like those might be the wrong answers, but I'll leave those there, and maybe I'll check later and see if I need to make some adjustments. Okay, so we've got v1, v2, v3. We've got our orthogonal basis. And by the way, we can do the same thing here if I wanted to, if I was going to do something else with this, which, spoiler alert, we're about to do something else with this. I could, again, multiply everything by 6. So if I multiply by 6, this would be 9. Is that right? Hold on. Yeah, 9, negative 7, negative 1, negative 1. So we could use just that simpler version of that. Okay. Yeah, okay. All right, so there is now our orthogonal basis. Now, what if instead of an orthogonal basis, we were asked to find an orthonormal basis? Well, the same is true. I mean, the work would be no different up to this point. We would start by finding the orthogonal basis. And now orthonormal basis means now we need to put all these as unit vectors. So we found that v1 was the vector 1, 1, 1, 1. We found that v2 was the vector negative 3, 1, 1, 1. And we found that v3 was the vector 9, negative 7, wait, yeah, negative 1, negative 1. You know, it occurs to me I could check this really quick. If I were to do any of these dot products, they should all be 0. So if I did v1.v3, I'm going to get 9 minus 7 minus 1 minus 1, which is 0. Good. If I did v2.v3, I'm going to get negative 27. No, this is wrong. I made a mistake somewhere. Hold on. Definitely made a mistake. Hold on. v3.v1. Oh, x3.v1 is 2. And v1 is 4. Okay, so I think that one's correct. And then x3.v2 x3.v2 is 0 plus 0 plus 1 plus 1, which is 2. And then v2.v2 would be 0 plus 1 would be 3. Okay, hold on. Right on the 1/2. Oh, I know what I did wrong. Hold on. You guys are probably yelling at your screens right now. Sorry about that. I think that one was correct, but that's all right. Let me just erase a lot of this stuff. All right, let me just erase all this stuff. You know, I could just go back and edit the video, but really, who has that kind of time? Okay, I was using the wrong vector. So x3.v2 would be 0 plus 0 plus 1 plus 1, which is 2. That was correct. And then v2.v2 would be 9 plus 1 plus 1 plus 1, which would be 12. Okay, I feel better about this. So if I bring in the 1/6, we get negative 1/2, 1/6, 1/6, 1/6. Okay, I'm feeling better about this. Okay, and then if I do all this together, I'm going to get negative 1/2 plus 1/2, so the top one is going to be 0. And the negative 1/2 minus 1/6 is negative 2/3. And then 1 minus 2/3 is 1/3. And then again, 1/3. Okay, and then once again, I can multiply everything by 3. So I could instead use the vector 0, negative 2, 1, 1. Okay, now let's double check this one more time. v1.v3 is 0 minus 2 plus 1 plus 1, which is 0. v2.v3 is 0 minus 2 plus 1 plus 1. Okay, this is better. This is better. Okay, so 0, negative 2, 1, 1. So let me change that. I apologize for the mistake. Sorry if you had to make any erasing or whatever. Anyway, back to our orthonormal, we need to find the magnitude of each of these. So the magnitude of v1 would be the square root of 1 plus 1 plus 1 plus 1, which is square root of 4, which is just 2. The magnitude of v2 would be the square root of 9 plus 1 plus 1 plus 1, square root of 12. And you can simplify that a little bit, but there's not much point. And then the magnitude of v3 would be the square root of 0 plus 4 plus 1 plus 1, which was the square root of 6. So my orthonormal basis, I'm going to divide each of the, in the first vector, divide everything by 2. And my second vector, divide everything by radical 12. And on my third vector, divide everything by radical 6. So 0, negative 2 over root 6, 1 over root 6, 1 over root 6. So now we have not only an orthogonal basis, but an orthonormal basis. And I think so far the only thing we found where that was useful was that whole U times U transpose that we had earlier in this lesson. Okay, let's take a look at one more example here. So let's define W as the null space of this vector, or of this matrix. And I'm just going to call this matrix A here for a second. So W is the null space of this matrix. Let's find a point in W that is closest to this vector 0, 0, 1, and then find the distance from X to that vector space. Okay, well, let's just find the null space first. Let's just start with that first. So I'm going to look at AX equals 0. So augmented matrix 1, negative 1, negative 2, 2, negative 2, negative 4, 4, negative 4, negative 8. Augmented that was 0, 0, 0. If I do some row operations, the first row is fine, and the other two rows just become a bunch of zeros. So this tells me that x1 is equal to x2 plus 2x3. x2 is itself, and x3 is itself. Okay. And so my solution here, x, is, I need a little more space. Okay, so my solution here, x equals, it'll be x2 times the vector 1, 1, 0, plus x3 times the vector 2, 0, 1. Okay, so my null space is, the basis for my null space are these two vectors, which I'll call x1 and x2. Okay, so we found my null space. Awesome. Now, if I want to find the point that's closest to x, that means I need to find x hat. And if I want to find x hat, I need an orthogonal basis. So I've got my x1, x2, that's great, but now I need to find an orthogonal basis. So v1, I'm just going to let it be x1, so that would be 1, 1, 0. And v2, we've already done this a few times. This would be x dot v1 over v1 dot v1 times v1. So x dot v1, that should be x2 dot v1. So x2 dot v1 is 2 plus 0 plus 0 over v1 dot v1, which is 1 plus 1 plus 0, which is also 2. Oh, once again, I messed up. I apologize. I forgot to use x2. Let's try, okay. Let's just start that over again. Come on, get out of there. All right, let's try this one more time. v2 is x2 minus x1 dot v1 over v1 dot v1 times v1. That looks better. Okay, x2 is 201 minus x1 dot v1. Nope. That should be x2 dot v1. Doggone it. x2 dot v1. All right, let's try this again. x2 dot v1 is 2 plus 0 plus 0 is 2. v1 dot v1 is 2. And v1 was 1, 1, 0. Okay, the fraction is just 1, so if I do the subtraction, I'm going to get 1, negative 1, 1. There's my x2. Yeesh. Let's make sure these are orthogonal. Do v1 dot v2. I'm going to get 1 minus 1 plus 0, which is 0. Okay. We now have our orthogonal basis. Now, I need to find x hat. I'm going to go to the next slide here. We said that the vector x was the vector 0, 0, 1. And we found that w was the span of my two. Now I'll use my orthogonal basis, which was 1, 1, 0 and 1, negative 1, 1. Oops, sorry about that. Okay, so then x hat would be x dot, and these are my v's, so it's x dot v1 over v1 dot v1 times v1 plus x dot v2 over v2 dot v2 times v2. Okay, so that is, let's see, so x dot v1 is 0 over, I guess I'll keep going, but it doesn't really matter, over 2 times v1 plus x dot v2 would be 1 over 3 times v2, which was 1, negative 1, 1. So this is the vector 1/3, negative 1/3, and 1/3. Of course, that first term is just 0 because it's multiplied by 0, so it doesn't matter. So there's x hat. Okay, now let's remember what this is. We've answered the first part of the question. The question said find the point in W that is closest to x. Well, that's this one. Okay, x hat is the point in W that is closest to x. Now we need to find the distance, which means we need to find x minus x hat. So x minus x hat. So if I subtract those, I'm going to get negative 1/3, 1/3, and 2/3. And then finally, the distance is the magnitude of that vector. So it would be the square root of 1/9 plus 1/9 plus 4/9, which is the square root of 6/9, or if you want to get really fancy, radical 6 over 3. Okay, so that is now the distance from x to that subspace W. Okay, so orthogonal spaces, orthogonal bases, I should say, and how they could be useful and how to find them. That is the end of the lesson. Thank you very much for watching.